Hello, young physicists. I'm shooting a little video here for you after class on a Wednesday, the 10th of February. I want to do a couple more of the problems that were in the PowerPoint style. The first that we alluded to on PowerPoint slide 9, I see that it is, and the second one is a little bit later down in the PowerPoint presentation. So this is just a little bit of a video for you to see me working a couple of problems. So slide 9, the second problem says a gas in a piston cylinder assembly undergoes an expansion process where PV to the 1.5 is constant. The initial pressure is 3 bars. Remember, a bar is an atmosphere. The initial volume is 0.100 cubic meters, and the final volume is 0.200 cubic meters. Determine the work done in the process. And we talked about this very briefly as we were getting out of the room so that the organic chemistry class could come in. So let's draw a diagram. Looks like this. Always draw your PV diagram first and ask what state variables you know and what state variables you don't know. So we're going from 1 to 2, like that. And we know that the volume at that point is 0.2 cubic meters, and the volume at that point is 0.1 cubic meters. And so we know that the work going from here to here is the integral of P dV going from here to here, right? We got that. So we know the work is the integral from V1 to V2 of P dV, and that is equal to the integral from V1 to V2 of C V to the minus 1.5 dV. Straightforward enough to do that integral. Raise it to the 1 more power, divide by that 1 more power, and so we get that the work that's done by the gas is C times V to the minus 0.5. Let's just go ahead and stick in our limits of integration. Minus V1 to the minus 0.5 divided by that minus 0.5. But one thing that's very helpful for us here is to recognize that P is equal to CV to the minus 1.5. So this is P times V. Okay? So this just looks like PV times PV. You see that this is, we can pull that out and say that CV2 to the minus 1.5, to the minus 0.5, excuse me, is equal to CV2 to the minus 1.5 times V2, right? But that's P2. So this is just equal to P2 V2 minus P1 V1 divided by negative 0.5. But we also know that P2 is equal to P1 times V1 over V2 to the 1.5. Okay? P2 to the, so that just comes from the fact that PV, as we stated in the problem over here, PV to the 1.5 is equal to constant. So P1 V1 to the 1.5 is equal to P2 V2 to the 1.5, and then I just solved that for P2. And we knew that P1 was, oh, we didn't, I had to solve for P1 here. To say that P1 is going to be, oh no, it's there, 3 bars, three atmospheres, and so P1 is going to be equal to 3.04 times 10 to the 5th pascals, newtons per square meter, and that P2 then is equal to 1.07 times 10 to the 5th pascals. And we put all that together. We stick this down in here, and we get that the work is equal to, the work is equal to 1.07 times 10 to the 5th pascals times 0.2 cubic meters minus 3.04 times 10 to the 5th pascals times 0.1 cubic meters, all divided by negative 0.5. And that is equal to, the board's so small in my office. I have to write big so you can see it on the video. And the board's not huge, so I'm trying to cram this stuff in here. When I stick those numbers in, I get 1,800 joules, 1.8 kilojoules. So I get 1.8 kilojoules, something along those lines. So see if you can follow that through and see if that makes sense to you as the way to do this kind of problem. So that's problem number 1 I want to do for you. That's the second problem on slide 9 from the PowerPoint for today, Wednesday the 10th. Let's go and look at, I think it's slide 14. I might have to poke around a little bit. Yeah, it's slide 14. Look at me remembering the stuff that's going on. So in slide 14, I want to point something out to you, how you treat areas. You know, we said that the pressure is, the work done is the area inside the curve, right? Area under the curve, or the area inside the closed loop. But how do you treat those when you have to deal with the fact you got funny shapes, like a circle or a semicircle we'll look at in this case, and the fact that the axes don't have the same units. You have to be very careful about how you go about doing that. So what I would look at here is, I would say that, let's look at problem 68. If I can read problem 68, it's very small. Let's look at problem 68 on slide 14. And it's that diagram that's on the right. And the diagram on the right is, looks like, I think I did this calculation someplace. Looks like this, where you've got the pressure here and the volume here, and you go from state 1 to state 2 in a semicircular path like this. And so the work that's done, how much work is done by the gas going from state 1 to 2. And there's a couple of ideas that we want to make sure that are clear on how you do this. So it's going to be the area that's inside here, right? The work done would be let's be careful about that. The work done is going to be the area that's under here, right? That's the integral of P dV, is the area that's under here, which is the work that you would get from this whole cylinder minus what's inside that semicircular area right there. Okay, so that's what you want to say. If you want to know the area that's under here, that area, the integral of P dV, is, well, that's P, is equal to the area of the big rectangle minus the area of the semicircle. So that's one problem-solving tip for you right there. Find the area under here by finding the area of the whole thing and subtracting out the area of the semicircle. You could just do the integral, but rather than doing the integral here, so if you knew how P was related to V by the formula of a circle, you can stick that in. You can do that integral, but you can avoid doing that integral by finding the area of this whole big rectangle and subtracting out the semicircular area that's inside right here, and that's going to leave you the area that's down underneath there. So that's what we got. That's what we want to try to do. The area of the big rectangle is, in this case, the limits are 1 liter to 10 liters. So that's 1 liter, and that's 10 liters out here. And over here, you've got the pressure is 6 atmospheres, 2 at the bottom. So this is 2 atmospheres, and this is 6 atmospheres. Okay, so this is what we've got, and so we would go in here and we would say, okay, the way we want to solve this problem is we want to find the area of the big rectangle, which looks like it's 9 liters times 9 liters times 6 atmospheres is the area of the big rectangle. Now, you got to convert atmospheres to pascals, and you got to convert liters to cubic meters. I'm not going to stand here and do this on the board. You could all go convert. So this has to be converted to SI units to get an answer that's in joules, okay? Then we have to subtract out the area of the semicircle. And the area of the semicircle, it has a radius that is both this and this. And that's your trick. To get the units right, you have to use one radius that's this and one radius that's this. So think of the area of your semicircle as 1/2 pi r. You're used to thinking of the area of a circle as pi r squared, but that's when the r in one axis has the same units as the r in the other axis. In this case, that's not the case. I got to use case twice in the same sentence. In case you can't use case twice in a sentence, you better case the thing out to figure out how you can use case more often. I would use it as an uppercase. But anyway, right here, we want to have that to be one of the r's and that to be the other of the r's. Okay? And so that r looks to me like it's 4 atmospheres. And that r looks to me like it's 4.5. It's half of that 9. So it's 4.5 liters. So it's going to be minus 4.5 liters times 4 atmospheres. Okay? And so times 1/2 times pi. So there's 1/2 times pi right in there. And so this looks like the answer is going to, that's all I'm going to do for you. You can do the rest of the working it out yourself, is to say convert your atmospheres to pascals, newtons per square meter, and convert your liters to cubic meters. And everything should work out for you here. Area of the rectangle minus the area of the semicircle is going to give you the area that's underneath that semicircle. So I wanted to show you that problem because there's a few little tips in there. There's a few things that you can use. This 2 really key things is to say you don't have to do that integral. Just take the 2 areas and subtract them out. And if you're doing something like a circle where you've got an r in one axis and an r in the other axis, you can't just use pi r squared. You got to use pi r to get the units right. Okay, that's what I got for you. I'm going to post this up on our internal site so you can go find this video and take a look at how to do some of these problems. Have a good afternoon, everybody.